Welcome to Lesson 2 of Module 2 on multidimensional data representation and manipulation. I am going to start with an important definitional question that I want you to think about throughout this lesson. What is the generic meaning of the verb pivot? What does pivot mean for a data cube? Lesson 2 continues your learning about data cubes from Lesson 1. In Lesson 2, you will learn about common operators to manipulate data cubes. The presentation in this lesson is informal to provide the central idea of each operator. In later lessons, you will learn how these operators are implemented in software to support pivot tables. You have two learning objectives in this lesson. In your own words, you should be able to briefly explain each operator. As part of your explanation, you should demonstrate each operator on an example data cube. We will consider common ways to manipulate the sales data cube presented in Lesson 1. Business analysts typically want to take a subset of a data cube, as data cubes with more than 5 dimensions are common in data warehouses. A business analyst may want to focus on a subset of dimensions, such as the products and locations for a single U.S. state, or a subset of member values for one or more dimensions, such as Western states and a location dimension. Business analysts also want to change the level of detail in hierarchical dimensions, such as moving from USA states to cities, or individual dates to weeks. The measure values in cells recalculate as the detail level changes. Business analysts may want to change the appearance of a data cube by rotating dimensions, such as changing the position of the location in product dimensions. Slice is one of the subset operators. Using the slice operator, a business analyst can focus on a subset of dimensions, replacing a dimension with a single value. For example, this slice operation replaces the time dimension with a single date, January 1st, 2017. This slice operation only shows the front face of the data cube with the first value on the depth or z-axis, January 1st, 2017. A variation of the slice operator allows the decision maker to summarize across members rather than focus on just one member. The slice summarize operator replaces one or more dimensions with summary calculations. The summary calculation often indicates the total value across members or the central tendency of the dimension, such as the average or median value. This example shows the result of a slice summarize operation where the product dimension is replaced by the sum of sales across all products. A new column called total sales can be added to store overall product sales for the entire year. Because individual dimensions can contain a large number of members, users need to focus on a subset of members to gain insights. The dice operator replaces a dimension with a subset of values of the dimension. This example shows the result of a dice operation to display sales for the USA states of Utah, Arizona, and Colorado for January 1st, 2013. A dice operation typically follows a slice operation and returns a subset of the cells displayed in the preceding slice. Business analysts often want to navigate among the levels of hierarchical dimensions. The drill down operator allows analysts to navigate from a broader level to a narrow or more detailed level, such as navigating from product group to individual products. Roll-up is the opposite of drill down. Roll-up involves moving from a more detailed level to a broader level of a hierarchical dimension. For example, an analyst may roll up sales from daily to quarterly level for end-of-quarter reporting needs. This example shows a drill-down operation on the state of Utah of the location dimension. The minus sign by Utah indicates a drill-down operation has occurred. Note that the sales value for Utah, 40, has been distributed to the 3 cities, Salt Lake, Park City, and Ogden. A roll-up operation is the reverse. To roll up, the minus icon toggles to a plus to eliminate the city details and sum the measure values in the cities. The pivot operator supports rearrangement of the dimensions in a data cube. For example, the position of the product in the location dimensions can be reversed in a sales data cube so that the product appears in the columns and location on the rows. The pivot operator allows the dimensions to be presented in the most appealing visual order. This table shows a convenient summary of the common data cube operators. Many other operators have been proposed, but are not in common usage. Lesson 2 extended coverage of the data cube model from Lesson 1. In Lesson 2, you learned about operators for subsets of data cubes, navigation and hierarchical dimensions, and rearrangement of dimensions. The presentation in this lesson was informal to communicate the central ideas of each operator. In other lessons of this module, you will see a data cube language and tools for graphical representation and manipulation of data cubes. In answer to the opening questions, the common meaning of the verb pivot is to rotate an object around a point. In basketball, pivot means to keep one foot in place while holding the ball and rotating the other foot. In baseball, pivot means to change directions using the base as a pivot point to make the final throw to complete a double play. As a youngster, I had trouble with executing double plays because I thought that pivot meant to jump while throwing a baseball. I confused changing direction, that is pivoting, with the aftermath to jump to avoid the spikes of the opposing player trying to append the double play. The pivot operator means to rotate a data cube. In data cube software tools, however, pivot involves rearrangement of dimensions rather than rotation. On data cubes of more than 2 dimensions, multiple dimensions appear in the row and or column area because more than 2 dimensions cannot be displayed in other ways. For example, to display a data cube with location, product, and time, the time dimension can be displayed in the row area inside the location dimension. A pivot operation could rearrange the data cube so that the location dimension displays inside the time dimension.